the last lecture, we critically reviewed the Coulomb's law of friction. Today, the plan is, in this lecture, the plan is to take some examples to illustrate the correct way of analyzing problem with friction. So, first example is something that is quite familiar to you. It is a block on an inclined plane problem, but I am sure that at the end of the day, end of this analysis, you will find something surprising about the same problem. So, the problem is the following. So, we have a block of mass m. So, this is a block of mass m on a fixed plane inclined at an angle theta. Now, in addition to your, this is what your standard block on a plane problem, but here we have some extra force. So, you apply a horizontal force mg. So, this you apply a force or horizontally on the block as shown in this picture, and the force happens to be, it's a special force, it's special magnitude, it happens to be equal to the weight of the block, but in the horizontal direction. Assume that the friction between the block and the plane is large enough to keep it at rest. So, this is still a statics problem. So, the block is motionless. The question is, if the coefficient of static friction is mu, for what range of angles theta the block will remain at rest? Note that it does not ask for a single value of theta. So, range of theta. So, this is the question. Now, before we start to analyze it, I want to mention one point, that normally, and as we have done also, that when we draw this, think of this inclined plane, we assume that the value of the inclined plane, the angle of the inclination is less than 90 degree. But in real life, you often encounter inclined planes where the value of the inclined plane theta is actually 90 degree or can be even bigger than 90 degree. For example, as shown in this figure, this angle is 90 degree, and in this case this is theta, and this angle theta is actually greater than 90 degree. Now, imagine that there is an ant which is standing still on a wall. So, this vertical position could be something as an ant on a wall, and similarly the this situation where angle is greater than 90 degree. If you still are not still convinced that angle can be actually greater than 90 degree theta, so look at this picture of a tree branch, and this is a kind of a natural example of an inclined plane. So, this tree branch represents the inclined plane, and in this case the angle is continuously varying, and in fact if you look at this part of the branch, the angle with the horizontal is actually greater than 90 degree. So, anything like a bird which is sitting on a tree branch at different position can be our block on an inclined plane problem. So, how do we analyze? So, let us analyze this situation using the free body diagram method. So, we are going to take the block as our system. So, there are three forces from the surrounding. So, one is the earth. So, this earth exerting the weight mg, which is downwards. Then the second is the contact force, which is has two components, the N and the F. So, I am going to use a notation of capital F for friction. So, this horizontal component, which is so as shown in this figure. So, this N is in the direction normal to the inclined plane, and the horizontal component F is in the direction which is parallel to the inclined plane. And then as given in the problem, there is an external force which is also happens to be equal to mg. So, if we draw the forces, the magnitude and the line of action and all these things. So, imagine this is the center of mass of the block. So, this is the weight acting downwards. The contact force has two component, normal component in the normal direction and the horizontal component in the horizontal direction, and then this represents the external applied force mg, and in this case our coordinate system is such that, so we are going to represent the direction parallel to the surface as let us say x axis and perpendicular to the inclined plane as y axis, and we are going to resolve the components of forces parallel to the plane and perpendicular plane as is the easiest or natural, as you have already know. Then, so once we have this free body diagram, then we apply the condition of mechanical equilibrium, that the all forces that are parallel to the surface, sum of all forces parallel to the surface must be 0, and sum of all forces perpendicular to the surface must also be 0. In this case, all the forces are passing through the same point, which is the center of mass of the block. So, we do not have to, so the torque due to all the forces are automatically balanced. So, we do not have to consider a separate torque balance, and applying this condition we get equation. So, this mg sin theta, which is coming from the weight, and this mg cos theta is coming from the applied force. So, this is weight, this is applied force, and similarly in the normal direction we have the normal component and this mg cos theta, which is coming from the weight, and this mg sin theta, which is coming from the applied force, equal to 0. So, we solve them. So, this equation gives us an expression for the frictional component, this equation gives us an expression for the normal component, and we get f is equal to mg sin theta minus mg cos theta, and n is mg cos theta plus mg sin theta. So, we have an equation for f and n. So, do you know the magnitude of f and n? Answer is yes. If the theta is fixed, then this is the answer for f and n. But the question asks that what is the range of theta, which means theta can vary. Why can theta vary? Because the frictional force is kind of self adjusting. So, its magnitude, so Coulomb's law says this magnitude can be anything which is less than or equal to mu times n. So, that means if I plug it these two expression and combine it with Coulomb's law of friction, we get an inequality that, and so to represent the magnitude we use this modulus sign, that the magnitude of friction is less than equal to magnitude of the mu times the magnitude of the normal component, the force. So, that gives a range for theta, because so there is a upper range of theta such that if the frictional force varies from 0 to mu n, that is why theta is not unique. There is a range over theta over which the friction force, so the block will be at rest and the frictional force and normal force will be given by these expressions. So, then with this equation, and note that the mg gets cancelled on from both sides from this equation. So, our answer, the range of theta, does not depend on m and g. It is kind of interesting to note. So, now we can simplify this further. So, this first we have to remove this magnitude. Now, there are two cases we will consider first. So, first let us assume that theta is less than pi by 2, the 90 degree. So, in that case the cos theta is positive, but still this, when we remove this magnitude, sin theta can still be greater than cos theta or less than cos theta. So, first let us consider the situation where tan theta is less than 1, which means sin theta is less than cos theta. So, in this case our mod sin theta minus cos theta is actually will be cos theta minus sin theta, which is less than equal to mu times sin theta plus cos theta. So, if I divide both sides by cos theta, which I can do because it is a positive number, so then we get 1 minus tan theta is less than equal to mu times tan theta plus 1. Now, if I rearrange terms, we get tan theta times 1 plus mu. So, take tan theta on the right hand side is greater than equal to 1 minus mu. Hence, we get this inequality that tan theta must be greater than equal to the ratio of 1 minus mu divided by 1 plus mu. Similarly, in the other case, when tan theta is greater than 1, in the same way you can show that we get a condition that tan theta must be less than equal to another ratio 1 plus mu divided by 1 minus mu, which happens to be the inverse of the previous ratio. So, these are equivalent to the condition that Coulomb's law that F is less than equal to mu times n. So, if we combine them together, we get a double inequality that the theta should be such that the tan theta is falls within this ratio 1 minus mu by 1 plus mu and 1 plus mu by 1 minus mu. So, this is the answer. Now, so you can ask that okay, so this is fine and we have seen this kind of problem before, where is the surprise? So, let us and now realize that, so we determine this theta in terms of mu, but realize that in a given situation the theta and mu are independent. So, what do I mean? So, you can vary the angle of inclination, anything you can choose given a block and a mu, which means because you know that mu depends on the nature of the surface contacts, the material of the contact surfaces. So, let us say if a block is made of wood and the inclined plane is made of let us say concrete, then the mu is fixed. So, and then you can change the inclined plane. So, you can vary theta at constant keeping mu fixed, and you can also do the opposite, like you can keep theta fixed and vary mu by changing the material of the block or the material of the inclined plane. So, theta and mu are independent parameter. So, then in that kind of situation it is very useful to sort of explore what is called the parameter space, that is you draw mu as your x axis and tan theta on the y axis. So, instead of theta we consider we use tan theta for mathematical simplicity, because we know the expression for tan theta. Then we can draw these functions 1 minus mu by 1 plus mu. So, this curve, this black curve which is decaying, represents the function 1 minus mu divided by 1 plus mu, and this green curve represents the function 1 plus mu by 1 minus mu. So, first consider the case where the angle can be is less than 90 degree. So, the angle of inclination varies from 0 to 90 degree, less than 90 degree. So, let us say now if we take mu equal to 0, which means a frictionless surface, no friction is present, then it gives you that there is only one value of inclined plane angle possible for which the given arrangement. So, for your reference I have shown the arrangement of the situation that we are analyzing. Only for theta equal to 45 degree the block will be at rest, because for any other value of theta the force will not balance in absence of friction, and hence the block will start to move up or down. That is the first thing, and I am sure that you may not have thought about that without looking at this. It is not very clear when you are not looking at this kind of picture. Then suppose you are increasing mu from 0 to sort of start to make the surface frictional and gradually more and more frictional. Then our inequality say that the range of theta is, so there is the range of theta is shown by, so the tan theta can be less than this curve, upper curve, and limited between the bound from the above and below by these two curves. So, these are the possible ranges, and what you can see is that as you increase mu, then the range of allowed values of theta becomes bigger and bigger. Then what happens when mu equal to 1? So, then this inequality shows that tan theta goes to infinity. Tan theta is infinity when theta is pi by 2, that is a complete vertical case. So, that means any value of theta is possible from 0 to pi by 2 if mu is 1. One more even more interesting is the case, if you consider the case when mu is bigger than 1, which means the friction is now dominating the normal component. In this case, if you go back to the analysis, this starting from this particular case, in this case it will be easier to look at it is easier to sort of start from the starting and take this kind of example and consider analyze the problem in terms of beta, which is pi minus theta, and rewriting the analysis. And in this case you will easily following the same route, you can easily show that the inequality that will be valid is that tan theta is less than this 1 plus mu by 1 minus mu. The other part of the inequality will not be relevant. So, the only case you need to consider where is that when is this particular case. So, this means now when theta is bigger than 90 degree, then tan theta is a negative number. So, and you can immediately see that let us say if you take theta as something like little bit less above 90 degree, then tan theta you can easily check is a huge negative number. So, that represents this part. So, this curve actually goes, so it diverges asymptotically, goes to infinity. So, at when mu equal to 1 it again diverges. So, this is the region where allowed values of theta. Now, what happens when mu tending to infinity? What we see here that when mu tending to infinity, then this curve approaches the value minus 1, which means tan theta is minus 1, which represents theta to be 135 degree. So, this represents that no matter what is your coefficient of friction is, if you consider this kind of situation, then the highest value of inclined plane possible for which this block will remain at rest, no matter what friction coefficient you have, is only 135 degree. If your angle of inclination is bigger than 135 degree, then this block will always move. So, I am sure that this is a kind of not at all obvious when you analyze the system, and so this is a important useful trick that I want to sort of tell you, is that when you have some parameter, control parameter in your problem, identify what are the control parameters are and then explore the full range of the control parameter. It often leads to surprising insight. Now, of course, I must mention that if you take, so this is true given the special value of this external applied force, which happens to be equal to the weight of the block. If you change that, if you take a applied force has a different magnitude, of course, the conclusion, the value highest value of the angle possible will be different. So, now I hope that you got something surprising out of a very simple familiar situation. Now, let us take another example, which is sort of some simple application of friction in day to day life. So, this is something called a ladder support. So, the friction between a ladder and the floor. So, the problem is the following, that there is a ladder AB whose length is 4 meter and mass is 15 kg, and it is at rest on these two surfaces, two walls, the floor and the wall as shown. Now, this red represents some person, a painter maybe, who is climbing the ladder, and the mass of this painter is 90 kg. Now, the ladder is a mechanism that top there is a roller, and the coefficient of static friction between the ladder and the ground is 0.25 is given. So, the question is determine the maximum distance s. So, from the floor along the length of the ladder, what is the largest distance s that the painter can climb without causing the ladder to slip at its lower end A. So, those of you who have climbed the ladder, this is a familiar scenario, and we want to compute this distance s. Now, we are going to sort of give you, so again we are going to use this force balance and torque balance approach, and sort of quickly sort of go through the state and maybe the equations. So, let us see, let us take the ladder, so our system is the ladder, then the surrounding is of course everything else, which means the earth, the floor and the wall. So, what are the interactions? So, the interactions so ladder plus painter, because we need to keep the painter in mind. This is our system, the combined system of small m and capital M. So, the interactions on this combined system is the weight, the force due to the earth. Now, where is this force going on? So, for simplicity we have represent this person by a line to indicate this is the line of action of the force. So, passing through, so this line passes through the center of mass of the person. So, let us say this is the center of mass, then the force, the weight of this person is something like mg, and this is the, so this is the line of action of the this weight. Let us say that this distance, let us call that c, where it hits the floor, and let us say that this distance AC is x. Then by from the picture it is clear then that, so this is x meter. So, let us say that this distance will be 1.5 minus x meter. The other interaction is the contact force between the floor and the ladder, which in general has two component, the normal component and the frictional component. Now, what is the direction of friction? So, if the ladder slips, then it will slip in this direction. So, the relative velocity is this direction. So, that means the frictional force must be in this direction, which is opposing that from that to happen. Now, the other contact is with at the point B, and here the problem says that there is a roller. So, the significance of this roller is that there is no it cannot support, this contact cannot support a force in parallel to this this plane. It will start to roll. So, it is a completely frictionless contact. So, the only force that is possible is, let us call that in B and let us call that in A, let us call that Fa. So, these are the forces on the system. Now, what about the weight by the, note that the weight by of the ladder passes through its own center of mass, and for simplicity, so this is the mg center of mass, and this line of action and the line of action of the weight of the painter does not follow the same line in general. So, if what is the line of action of the weight of the ladder? So, by symmetry we can assume that this center of mass is at the midpoint of the ladder. So, then if I draw this picture clearly, So, this is 1.5 meter, this is the ladder, then this is the midpoint, and then by geometry it intersects this floor at the midpoint between the distance from A, let us call that P, midpoint of B. So, AP is 1.5 meter. So, this point must be 1.5 meter by 2, and let us call that S. So, this S is, let us call that S. So, this is the line of action. So, this point is C. So, this AC is X. So, now we write down the condition of equilibrium. So, the force balance and torque balance. So, first force balance, let us take this as our x axis and this as our y axis. So, let us consider the total force on the x direction must be 0. So, the sum of all force in x direction. So, there is a force on this combined system is F A and N B, this is 0. This gives you an equation that F A is equal to N B, they cancel each other. Similarly, the total force on y direction is N A minus M G minus small m g, which is the weight of the ladder, and this is equal to 0 for force balance, and that gives you an expression for N A. So, let us ask what are the unknowns in this case. So, the unknowns in this case are the 3 unknowns. So, the contact force at A, NA and FA, components of contact force NA and FA, and components of contact force NB at the contact B. So, we have 2 equations and 3 unknowns. So, we need one more equation that comes from the torque balance condition. Now, note the torque balance condition. So, let us consider that we have our pivot point is B. So, we are computing the torque around the point about the point B. So, the line of actions of NB passes to the pivot point B. So, that will not contribute any torque. So, all other forces will contribute any torque. So, you can check for yourself, you can analyze this problem from other pivot points and you will arrive at the same answer. So, let us say MB. So, what is the torque due to the force A? So, this is effectively a 2D problem. So, the moment of force or torque is very simple, it is just the distance between the line of action from the point B, perpendicular distance, times the magnitude of the force, and the direction of the torque is either perpendicular to the screen, either going upwards or going downwards. That you can determine from the right hand thumb rule. So, the contribution torque due to NA is this NA times 1.5 meter. Now, this is in a clockwise direction, let us call that negative. The torque due to the weight of the painter is in the opposite direction. So, this is mg times 1.5 minus x, and the torque due to the weight of the ladder is mg times 1.5 divided by 2 meter, and the torque due to the friction is this height h. So, plus F times h, and this torque is balancing. So, they are 0. Now, we can simplify it little bit. So, use this condition, so that we get that. Now, note that from the problem, so h is known. So, h is from geometry, this is 4 square minus 1.5 square, and the unit is meter, and this turns out to be 3.71 meter. So, now we have F times h, F A times h minus m plus small m times g times 1.5 meter plus mg times 1.5 minus x meter, let us call that meter, plus mg times 1.5 by 2 meter is equal to 0. So, let us simplify this further. So, let me write it here. So, we have f a times h minus m g into 1.5 minus m g x plus m g into 1.5 by 2 equal to 0. So, then we have x which represents the line of the distance of this line of action of the center of mass of the painter. So, we get an expression for x which is given by f a times h minus m g 1.5 divided by 2 and divided by m g. So, this represents x. Now, you can see that the small m g and capital M g. So, this term is a constant, this term is a constant. So, x is basically depends on the f a. So, if more bigger the f a, the more away from x this line of action. If f a is small, it is closer to this point of contact A, and f a is big means it is going further and further. So, as the painter climbs on the ladder, so this point line of action, the distance between the line of action of the weight from this point contact point A becomes bigger and the frictional force is also bigger. So, then but the painter cannot climb indefinitely all the way till the contact point F, because F a is limited by this Coulomb's law, which is given by this expression. And then we know that from our analysis that this is m plus m times g from force balance condition. So, we get x is equal to mu times m plus m g. So, x must be less than or equal to this value. So, now you can cancel the g. Now, if you plug in all the values, then you get x to be something like 0.957 meter. Now, this is x, but what you want to know is s. So, that we can get from geometry. So, this is A, this is B, this is x, this is C, this is B, this is x. So, we drop a perpendicular and this angle is theta. So, you can see that this distance from this geometry, this s by x is given by AB by AP, which is 4 meter by 1.5 meter, and from that you get x to be 2.55 meter. So, plug in the values of x, AB and AP, you get that answer. So, now this important point is that this is the maximum value the painter can climb. After that, if he climbs or she climbs higher, then the ladder will start to slip. But this is an experimental demonstration that the painter position can be anything from the floor up to this distance, anywhere, and if the painter's position is lower than this value of 2.55 meter along the ladder, that means that from this analysis we can see that it means that the frictional force is also less than this value of mu times Na. So, mu given, because no matter, you see from the force balance, the Na is constant. No matter where the painter is climbing, Na is always remains the same. Mu is also constant. So, mu times Na is a constant value, but that means that the friction, can vary. So, the fact that the painter can climb from up to a certain distance s, not just one particular value of s, but a range of distance it can cover, on the climb from on the top. So, this is actually directly demonstrates that friction is a self adjusting force and its magnitude can vary from 0 up to a certain maximum. So, now I quickly mention the another exercise for you to try. So, this is you can do it in a same way. So, there is a block, a homogeneous rectangular block of mass m and width b and height h placed on a horizontal surface, and there is an external force P, and this force is moving the block along the surface with a constant velocity. The coefficient of kinetic friction is mu k. So, we have to determine the greatest value, again the emphasis is on the word greatest value h. So, where h represents the height of the line of action of P from the floor may have, so that the block will slide without tipping over. So, tipping over means if you have this block, so tipping over means it will go like this, and suppose if h is the middle of the point of application of the force h is precisely at the middle of the block, what is the location of the point C on the bottom face of the block through which the resultant of the friction and normal force acts. So, I leave it as a take home exercise for you to practice the free body diagram and to analyze the friction correctly. So, to summarize, these problems are meant to illustrate you how to analyze the friction problems correctly. So, you have to remember that friction force is a self adjusting force which can vary within a range, and the mu can have any value between 0 to infinity. In the next lecture, we are going to consider the friction between a solid and a fluid, that is the drag force. Thank you.